What's up, physics nerds? Welcome to the circuits review video. I decided to put this out early because I feel extra motivated to be productive today. I got my cup of grass jelly green tea with me and I'm ready to do this review video. Alright, so here's our list of topics. We're going to start with series circuit, parallel circuit. Then we're going to talk about the electric meters, ammeter and voltmeter. And then next we're going to look into the combination circuits and finishing up with some tips on how to use the reference table. Yes, that is a necessary slide, guys. Before we even get into some of the topics, I want you guys to imagine this. A circuit is like a roadway. And so what is going to be our cars? We're going to imagine the electrons, the individual electrons that flow through the circuit as cars driving down a roadway. And so when you have that flow of traffic, then that's what we call our current here. And then if you notice, we have toll booths in our highways in order to get through bridges, tunnels, etc. And in our circuit, we're going to use toll booths to represent our resistors, because you can't get through resistors unless you pay a fee at the toll booth. And what is that fee we're going to pay? Voltage. In order to pass through resistors, you need to have a certain voltage fee. And here in our circuit, voltage is like our currency to pass through those resistor toll booths. And then lastly, we have the battery, which is your home. That's where you replenish all your voltage and your money. I hope that was a helpful analogy. Now let's begin. So a series circuit. Here we have resistors connected in a single pathway. So here we have our battery, we have one resistor, we have a second resistor, and a third resistor. Notice how they're connected in a single pathway, one after the other. That's what we mean by series circuit. Here, regardless of where you are on the circuit, over here, if you're here, 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 or here, the current is the same throughout because the same traffic flow is going through the same pathway, same road, same lane. So regardless of how much current you have, whatever it is, it flows the same through each resistor. Okay. Now lastly here we have voltage drops. So it's our voltage, the total voltage you start out with drops after each resistor. So let me show you an example here. So let's say you have 12 volts in this battery. And here you got some of these resistors. Let's say you have 1 ohm, you have 2 ohms here, and 3 ohms here. So, first of all, we need to figure out what is our equivalent resistance. So equivalent resistance here in our series circuit is simply the sum. So Req equals the sum. Okay, I hope I did that notation correct. So in our example here, we take 1 ohm plus 2 ohms equals 3 ohms. Oops. Oh. It's supposed to be plus 3 ohms. So that total right here is 6 ohms. So 6 ohms is our total equivalent resistance. That's the overall resistance in this circuit. So 12 volts has to push through 6 ohms of resistance. Now how do we figure out what's our current here? What's the current in this circuit? Well, that means we have to resort to our handy dandy Ohm's law. Okay, so we have 12 volts of voltage here, and we're figuring out what is our overall current going through the circuit. And so here, when you talk about overall, you're going to use your equivalent resistance here. 6 ohms. So we get a current here of 2 amps. So 2 amps of current is flowing through this entire circuit. Now I'm going to go focus back here on voltage drops. So what is the fee we have to pay to pass through each resistor? And that depends on the resistance. So less resistance requires less voltage, whereas higher resistance requires more voltage. And so that you have to resort to using V equals IR once again. Let's do it over here. So if we have 2 amps flowing through this resistor, and we have 1 ohm going over here, that means we have 2 volts going through V1, going through our first resistor. So you have to pay 2 volts to get through there. So you start off here, going through here, you start off with 12 volts. And then after you pass through the first resistor, you have to pay 2 volts. So what does that mean you're left with? Over here, you're left with 10 volts. Now getting through this 2 ohm resistor, we got to figure that out. So 2 amps times 2 ohms, following the same formula, you have to pay 4 volts. So 10 minus 4 is 6 volts. Now passing through this last resistor, 3 times 2 amps, you're left with, you have to pay 6 volts, and after here you're left with 0 volts. That is standard for voltage drops. That when you come out of the battery, you start with the full amount of voltage, and after each resistor you drop, you have to pay voltage to get through each resistor. And so by the end of it, you should pay all of your voltage until you're left with 0, and going back to the battery to replenish your total. So it goes through this entire loop over and over again, spending until you get back home to your battery and you replenish your money and go back again through the loop. Sounds like a sad life for an electron in a circuit. Next, we have the parallel circuit. Here, resistors are separated into multiple branches. So here's one, oops. Here's one, here's two, and here's a third one. Okay, so notice here, the current flows out of the battery and then it splits up into 3 different branches until they all meet up once again, coming back. Alright. Now what's different here is that the voltage is the same across the branches. What do I mean by that? So let's say once again we start out with 12 volts in our battery, flows out of the battery, and then once it reaches this point, the voltage is the same in each branch. So 12 volts flows through here, 12 volts flows through here, and 12 volts flows through here. It's not like the current where it splits up depending on the resistance. Instead, it's going to be the same voltage in each battery. Okay. Now let's put some values here. So let's pretend we have 6 ohms here, 6 ohms here, 6 ohms here. Alright, now, finding the equivalent resistance is a lot different for a parallel circuit. This equation right here is very different. And so on and so forth, depending on how many you have. Now, in this example, we have 3 6 ohm resistors. So when you do this math, this is simple to deal with. So 1 over REQ is equal to 3 over 6. But then we got to flip it. So REQ, equivalent resistance, is equal to 6 over 3, which is equal to 2 ohms. Now, you don't have to use this equation if you're looking at resistors that are of the same value. So we have 3 identical resistors split into 3 branches. The shortcut is to take that value and divide it by the number of branches. So 6 ohms divided by 3 branches, that is equal to 2 ohms. And if you use the equation, it's the same answer. Now let's say you have 2 branches instead. 6 divided by 2 branches, you get 3. And you'll get the same answer if you do the same equation. Now notice here, our overall resistance is less. In the series circuit, our overall resistance is higher. In a parallel circuit, you want to reduce the resistance. So that's why parallel circuits end up with less resistance if you use the equation. And also the purpose of it is to divide up the traffic flow to make it less heavy in the traffic. If you add more and more lanes, you allow cars to move through faster. You decrease the resistance and allow faster current, more current to flow. Now once again, let's put an ammeter here to measure our current. How do we find the total current in a circuit? So we have total current. We still got to use Ohm's law. V equals IR. 12 volts we have. We're solving for I. And it's still, once again, we're using the equivalent resistance. That's our total because we're figuring out the overall picture here. She gets 6 amps. So notice here we have higher current. 6 amps of current flowing through. So 6 amps of current starts out right here, coming out of this battery. Now once it reaches this point, it's going to split up. And how do we even figure that out? So first we have to start out with the same idea that it's the same voltage throughout. So 12 volts flows through each branch. So V equals IR. 12 volts is equal to I1. We're figuring out what's the current in the first branch, times our 6 ohm resistor. We're figuring out what is going on in that specific branch right here. So that's when you start to use the individual values. 12 divided by 6, I1 is equal to 2 amps. So 2 amps flows through here, and because they're all the same numbers, 2 amps here and 2 amps here. So this is going to go into Kirchhoff's law, current law. We have 6 amps flowing into this point, and then it starts to split up. So 2 amps, 2 amps, 2 amps. After they flow through each branch, they all meet up once again at this point. They add up. So the total current that goes in should be the same total that goes out. So 6 amps flows in, and 6 amps should still flow out, back together. So back here, 6 amps. Okay. Now if we focus on the voltage drops, once again we have 12 volts flowing through each branch. 12 volts pushes through here, 0 volts left, pushes through here, 0, pushes through here, and it's 0. So even the voltage law still holds here. You spend 12 volts in each branch total. You spend all of your voltage, come back here and through the battery and start over again. Now a few other notes here about parallel circuits. So the equivalent resistance is always smaller, always less than smallest resistor. So here 2 ohms here is smaller than our smallest resistor of 6. Even if you have different kinds of resistor values, 3, 6, 9, if you have, for example, 3, 6, 9, then your overall resistance is going to be less than 3. It's always smaller than your smallest resistor. Because the purpose of putting things in parallel is to decrease the resistance and increase the current. Alright, now let's get into the differences between the 2 meters. So we used ammeters to measure current and voltmeters to measure voltage. Ammeters are always connected in series. Why? Because they have 0 resistance. By having 0 resistance, you do not disturb the flow in the circuit. You're able to get by and pretty much be invisible in the circuit and not affect what's going on. So if you want to measure current going through the battery or through the resistor, you connect it in series to that. Whereas here for a voltmeter, you have to connect it in parallel to what you're measuring. So if you want to measure the the voltage going across a resistor, you got to connect it in parallel to that. So this voltmeter is going to be in a separate branch next to the resistor. Why is it in parallel? Because we assume it has infinite resistance. That means you can't get past it. In order to not disturb the circuit, you want to separate it from the circuit. Put it in a separate branch. That way it doesn't disturb what's going on. Now if you want to measure this across the battery, then you got to put that in parallel to the battery as well. Just like that. Now let's say you want to have both the current and the voltage readings. So this is what it's going to look like. You have a battery, you have an ammeter, you have a resistor, and you also have the voltmeter measuring the voltage across that resistor. So that's what it's going to look like if you want to measure both the current and the voltage across the resistor. Now combination circuits are its own very own beast. So you could have something like this. So notice here you have this part and you have this part. But then you have a parallel component in series with another resistor. So within, even with its own parallel component, you'll see here two resistors in series with each other, which is also parallel to another resistor over here, which this whole component is in series with this one. So a lot of working with combination circuits, knowing how to simplify it. So it goes, you just got to make sure you know how to simplify it, going one at a time. Then from here, you're going to go from, going to simplify that to this. And then from here, you'll finally finish off with a single resistor. So that's the aim of combination circuits. You start with this big monster and you simplify it little by little, combining two or more resistors at a time, either in series or in parallel to each other. So you see the progression here. And usually a follow-up question to finding equivalent resistance is to find the overall current going through the circuit. So if they give you the voltage in the battery, you found the equivalent resistance, then you could solve for the current going through the entire circuit. So we're looking at the overall big picture. Now we've reached this part of this PowerPoint using the reference table. So here's the first slide. What if I don't remember the circuit symbols, Miss Mapoy? Well, here you go, it's in the reference table. These are the parts of a circuit. If you don't remember what they look like, you'll most likely be using the battery cells, maybe a switch. This right here, this shows an open switch. So that's what it looks like when it's open. Remember, when it's an open switch, then you pretty much cut off the current. No current, closed, current. Okay. The next you have the voltmeter, the ammeter, as I said before, resistors. Variable resistor, we typically don't deal with problems like that. And lamps which is more prevalent to the labs we've done, but almost similar to resistor. Okay. So there might be a question that could ask you to draw things. So remember how to draw things, knowing the difference between series and parallel. Series, you connect them in the same path. Parallel, you have to create branches. Now this I think is most important here. What if I don't remember the differences between series and parallel, such as dealing with current, voltage, and resistance? So let me put a division line here. Separate it. Bam. So luckily this is in the reference table, and you just got to remember how to read these equations. That's important. So here for a series circuit, look at the current. I equals I1 equals I2 equals I3. So regardless of where you are in the circuit, if you want to measure the current across different resistors, it's all going to be the same. Stays the same. Whereas here on a parallel circuit, this shows that the total in equals total out. Or you could do the sum of the branches. Total in equals sum of the branches going out. Next is the voltage. So this is the sum of drops equals voltage in battery. Whereas here, this one stays the same in the parallel circuit, stays the same in each branch. And then here, the resistors, this is the sum. And then over here, this is the inverse of sums of inverses. That's a lot. Remember the calculator shortcut I showed you? So if we think back to the example I showed you with 3 6 ohm resistors like this. Oops, let's do 6 plus 1 over 6 plus 1 over 6. Another way I could show you guys in the calculator like this, if you plug it in, plug and chug. If you do that all in the calculator, you should get the same answer. Okay. So remember, you should know how to read these equations so that at least you don't have to be stuck memorizing what the differences are between series and parallel. Know how to read the equations and they should give you a hint as to the differences between series and parallel circuits. And now, some final words. What I totally advise you guys, absolutely you must do is use the reference table. I am not kidding. The reference table is your best friend. Do not be afraid to use that reference table. Embrace the reference table. It's your best friend. It shall help you through this quiz. And that's it. Good luck, guys.